2, 1 is a vector in F2, and we know it's a 2-dimensional vector. And it's pretty evident that F2 is a 2-dimensional space as well. Following that reasoning, space that contains 3-dimensional vectors is a 3-dimensional space. This applies up to Fn. But what if the vectors in question are not lists? With f to the s, for example, we cannot define dimension by element length. So how should we define it? In linear algebra, dimension is actually defined by the number of vectors required to span a space. Say for example, we have this point in R2, and we take the standard unit vectors, then it's easy to see this point can be represented by the sum of scalar multiples of these vectors. We call this point a linear combination of these two vectors. Regardless of the position of this point, we can always express it in terms of these two vectors. Now if we take a different set of two vectors, even if they're not perpendicular, they can still be used to express the position of that point. And this holds true regardless of the position of the point. So if we express this concept using set notations, R2 can be written as the set of all linear combinations of the standard unit vectors. It can also be written as the set of all linear combinations of those green vectors. Have you noticed the pattern here? It seems that if we pick two random vectors, then we can span R2. F2 can be spanned by 2 vectors, F3 can be spanned by 3 vectors, and Fn by n vectors. This concept is essentially the definition of dimension that we introduced in this chapter. We'll be building up to the definition of dimension through key definitions and theorems. Let's dive in. So what is a linear combination? We've actually already seen it through visualization. Now let's try to formalize it with math expressions. Let's say we have a list of vectors v1 through vn. Then by multiplying each of them with a scalar and adding them up generates a linear combination, where a1 through an are the coefficients. There you have it, the definition of a linear combination. As an example, 17, minus 4, 2 is a linear combination of these two vectors because we can find the right coefficients to generate it. 17, minus 4, 5, however, is not a linear combination of these two vectors because we cannot find the right coefficients. Now we introduce a closely related concept, span. Recall the definition of a linear combination. Suppose again that we have a list of vectors v1 through vn. The span of these vectors is just the set of all of their linear combinations, where the a's are just the coefficients. So that's it, the definition of a span. So going back to the previous examples, 17, minus 4, 2 being a combination of these vectors means it's in the span of these vectors. While 17, minus 4, 5 not being a linear combination of them means it's not in the span of those vectors. Now we introduce the concepts of finite dimension and infinite dimension. A finite dimensional vector space is a space that can be spanned by a finite list of vectors. Conversely, an infinite dimensional vector space is a space that's not finite dimensional. Let's walk through some examples. Fn is finite dimensional. To see why, let's suppose v is a vector in it. That means v can be expressed in this form, which can be written as a linear combination of the standard unit vectors, meaning it's within the span of those vectors, which is finite. So Fn indeed is finite dimensional. As another example, P of f is a set of all polynomials over f, so all of its elements can be written in this form, where the a's are just the coefficients that are taken from f. As an example, s cubed minus 7x plus 5 is an element of P of r, and 3 plus I times z squared minus iz plus 5 is an element of P of c. Now we're going to claim two things about P of f. First, it is a vector space. Second, it is infinite dimensional. Feel free to verify the first point using concepts from the first chapter. We'll focus on the second point. To see why P of f is infinite dimensional, let's try to think about this question. Can a finite list of vectors span P of f? Let's just take two random lists of vectors and see if they work. Just to clarify, in this case, each vector is a polynomial. So the one on the top is a list of 4 vectors, and the one on the bottom is a list of 3 vectors. Their linear combinations can be written like this, respectively. Now for each of these lists of vectors, we can find the vector of the highest degree. For the top one, it's x cubed. For the bottom one, it's x to the 100. If we take them and raise their powers by 1, we get x to the 4th and x to the 101, neither of which can be represented as linear combinations of the original vectors. So they're not within the corresponding spans either. So whichever list of vectors we choose, we can always find a vector outside its span, provided the list is finite. And that is why a finite list of vectors cannot span P of f. And therefore, P of f is an infinite dimensional space. So that's it, finite and infinite dimensions. Next up, we're going to look at a very important concept, linear independence. We've already seen that R2 can be spanned by 2 vectors. This point, for example, can be decomposed using these 2 vectors. But what if we have 2 parallel vectors? As you can see, every possible linear combination falls on this line, and they can't span the entire plane. Well, this is what we call linear dependence. But how do we formalize this concept? The definition goes like this. If the only way to write the 0 vector as a linear combination of a list of vectors is by taking all the coefficients to be 0, then this set of vectors is said to be linearly independent. To make it more concrete, let's go back to the example. If we take 2 and 1 as the coefficients, or we could also take 4 and 2. Both sets of coefficients generate the 0 vector. In fact, there are an infinite number of linear combinations that generate the 0 vector, and therefore, the 2 vectors are linearly dependent. Now, what if we have 2 vectors that are not parallel to each other? It's easy to see that there's no other way to get the 0 vector other than taking the coefficients to be 0. In this case, we call these vectors linearly independent. Let's again go over a few examples. It's easy to see the first 2 are linearly independent. The third one is a list of a single vector. In this case, it is only linearly independent if the vector is not 0. Lastly, if we have a list of 2 vectors, then linear independence only holds if each of them is not a scalar multiple of the other. Make sure you understand by working through the examples. With the previous concepts under our belt, we're ready to introduce the linear dependence lemma. What it states is that if we have m vectors v1 through vm, and we use this circle to represent its span, the lemma says that if these vectors are linearly dependent, there exists a vector, which we denote by vk, that even if it's removed, does not change the span of these vectors. The span doesn't get larger, doesn't get smaller either. Let's prove why that is the case. So let's start with a list of vectors v1 through vm, and let's assume they're linearly dependent. By the definition of linear dependence, there exists a set of coefficients, not all 0, that generate the 0 vector. This implies we can find the last non-zero coefficient, which we denote by ak. This implies every term after it is 0, so we can remove everything after it, giving us this equation. Now, because ak is non-zero, we can rearrange the terms to represent vk as a linear combination of the other terms. Since we don't care about the actual values of the coefficients, we can replace them by b1 through bk-1 to make things cleaner. So now we have vk written as a linear combination of the other vectors. Let's assume u is a vector in the span of the original list. This implies u can be written as a linear combination of v1 through vm. Then we can take out the term ck-vk and substitute the linear combination we just got for vk. Plugging this back into the equation only changes the coefficients of the terms preceding vk, but does not change anything after it. So we'll end up with an equation that looks like this, with d1 through dk-1 representing the new coefficients. ck plus 1 through cm didn't change, so we keep them as is. So now what we have is U represented as a linear combination without using VK. Now because U can be any vector in the vector space, this implies we can span the entire space without using VK, completing the proof. Let's restate this lemma for clarity. It states that if the list v1 through vm is linearly dependent, there exists an index k such that vk is within the span of the vectors preceding it. So that's it. Let's again use an example to make it more concrete. Given this list of 4 vectors, how do we determine if they are linearly dependent or independent? Let's try to apply this lemma. Let's start with k equals 1. There's no vector coming before it, so it's quite obvious it's not within the span of its preceding vectors. So k equals 1 doesn't work. How about k equals 2? Let's give it a try. It's quite obvious the second vector is not a scalar multiple of the first vector. No luck then. Let's try k equals 3. As you can see, the third vector can indeed be written as a linear combination of the first 2 vectors in the list, so we take k equals 3. This implies this list of vectors is linearly dependent. With this lemma ready, we can now use it to prove another very important theorem. This theorem states that a linearly independent list of vectors is never longer than a spanning list of vectors. In other words, if the length of a list of vectors is greater than a certain number, it is guaranteed to be linearly dependent. But what is this certain number? We'll address that later. But it's easy to see with R2, this number is 2. But for R3, this number is 3. For Rn, this number is n. Now that we understand what it means, let's go ahead and try to prove this theorem. We start with 2 lists of vectors, u1 through um and w1 through wn, with a list of w's spanning v and the list of u's being linearly independent. Now our goal is to prove m is no greater than n. We start by taking u1 and prepending it to the other list, giving us these new lists. The top list remains linearly independent, and the bottom one still spans v. Notice that the w part already spans v, so u1 is redundant in that sense, implying that this entire list is linearly dependent. By the linear dependence lemma, we can remove one vector from this list without affecting its ability to span the entire space. Now because u1 was taken from a linearly independent list, it cannot be the 0 vector, so the vector to remove must be among the w's. In other words, we can find a wk that is a linear combination of its previous vectors. This leaves us n-1 w's. For simplicity, we relabel the w's and use w1 through wn-1 to represent the remaining vectors. By the linear dependence lemma, we know that the resulting list still spans the space. Now we repeat what we've just done, prepending one of the u's and removing one of the w's. We'll eventually reach a point where there's only one u remaining. Again, we take that u and prepend it to the other list, and this again gives us a linearly dependent list. We originally assumed that the u's are linearly independent, so when applying the linear dependence lemma, the vector to remove will never be one of the u's, but the lemma guarantees the existence of the vector to remove, so it must be one of the w's. So we proceed to remove it and get this final list. As you can see, we're left with no less than 0 w's. There could be no w's remaining. There could also be some remaining. In either case, it's no less than 0, proving that m is no larger than n. This might seem unintuitive at first, so let me add some explanation here. In each step, we add one u and remove one w, and we end up with 0 or some w's, indicating there must have been as many w's as u's. So that's how to make sense of this proof. Let's again use an example to make it more concrete. This list of vectors obviously spans R3, so it's a spanning list. By our theorem, any linearly independent list of vectors must be no longer than this list. So for example, this list of vectors has length 4, so it's automatically linearly dependent without any calculation. As another example, this list of vectors has length 4 and is evidently linearly independent, so it must be no longer than any spanning list of R4. So let's say we have this list of 3 random vectors. Then we know that it cannot span R4 without any calculation required. Pretty convenient, isn't it? Up till now, we've covered chapter 2.8 of the text. Picked some exercise problems from the text. If you want to master these concepts, definitely give it a go. You might want to refer to the book for a more thorough understanding. With all the previous concepts under our belt, we're now ready to define what bases are. A basis for a vector space is a list of vectors that is both linearly independent and spans V. Let's walk through a few examples. This is a basis for Fn. We call it the standard basis. This list of vectors is a basis for F2 because it meets both the conditions for a basis. This list of vectors is not a basis for F3 because it does not span F3. This list of vectors is not a basis of F2 because it is not linearly independent. This list of vectors is a basis for P sub m of F. This sub m here indicates that this set only contains polynomials of degree at most m, so it's easy to see this basis indeed spans the space. Now let's solidify our understanding of bases by exploring its properties. First off, this theorem says that a list of vectors is a basis of V if and only if every vector in V can be uniquely written as a linear combination of that list of vectors. Let's go ahead and see why that is. Let's assume V1 through Vn is a basis, and let's try to prove every vector in V can be written as a unique linear combination. Let's assume V is a vector in the space. By definition, our basis can span V, so we know V can be written as a linear combination of the basis, but we don't know if this representation is unique. So let's assume some other representation also exists. Now taking the difference of the two equations gives us this equation. Because V1 through Vn is linearly independent, that means the only way to generate the zero vector is by taking all the coefficients to be zero. So we know a1 minus b1 all the way through an minus bn are zeros, meaning each of the a's equals each of the b's, proving the uniqueness of the linear combination. Now for the other direction, we first assume the uniqueness of the linear combination, and we want to show that this list of vectors is a basis. And to do that, we need to show this list of vectors is both linearly independent and spans V. Now the assumption that every vector in V can be uniquely written as a linear combination already implies this list of vectors spans V. So let's take that off. Now to prove linear independence, we know that a vector space must contain the zero vector, which can be uniquely written as a linear combination by our assumption. We also know that taking all of the coefficients to be zero is one way to generate the zero vector. Because we've assumed uniqueness, this must be the only way to generate the zero vector, and therefore linear independence holds, proving that our list is indeed a basis of V. This theorem tells us that we can represent any finite dimensional vector space by choosing a basis without running into the problem of having multiple representations of a vector. Here are two more important theorems about bases. The first one says that with any spanning list, we can get a basis by removing some of the redundant vectors in it, essentially making it linearly independent. The other one is pretty much the inverse of that. It says that we can make a linearly independent list a basis by adding some vectors to it. Now 2.30 can be proven in a similar manner. We prove the linear dependence lemma by removing vectors from a list. We won't go over it here. Feel free to give it a try. The proof for 2.32 can be done similarly as well. Now let's try to visualize the concepts we've learned so far. Let's say we have a list of m vectors, and we use the number line to indicate the size of m. Now let's say the length of the basis of v falls on this point, which we denote by n. According to what we've learned previously, if any list of vectors is shorter than this basis, we know it does not span V. Conversely, if it's longer than the basis, it might span V, but it's not guaranteed, because there might be some redundant vectors. And we also know that any list of vectors longer than this basis must be linearly dependent. And if it's shorter, it could be linearly independent, but it's not guaranteed either. With everything we've seen so far, you might have the intuition that since we know the dimension of f2 is 2, the dimension of f3 is 3, and the dimension of fn is n, does this mean dimension is just the length of a basis? To answer this question, we must answer another question first. Do all bases have the same length? Otherwise, we wouldn't be able to define dimension by the length of a basis. Fortunately, this turns out to be the case. All bases do have the same length. But before we get into why, here are the exercises for this chapter. Do give them a try. Alright, let's get to proving the theorem. To get started, let's assume B1 and B2 are two bases of V. By definition, B1 is linearly independent and B2 spans V. By 2.22, B1 must be no longer than B2. By swapping the roles of B1 and B2, we can get the opposite inequality. So if we combine them, it follows that B1 must have the same length as B2, proving that any two bases have the same length. With this theorem proven, we now have everything we need to define dimension. We define dimension by the length of a basis, and we denote the dimension of V by dim V. So for example, dim Fn equals n, and dim p sub m of f equals n plus 1, because its basis has length n plus 1. Let's also look at a few theorems to improve our understanding of dimension as well. This theorem states that every linearly independent list of vectors whose length happens to be the dimension of the space is automatically a basis. To simplify this long sentence, it basically says that linearly independence and the length equals the dimension of the space implies the list in question is the basis. The proof is straightforward. If we have a linearly independent list of vectors whose length is dim V, by 2.32 we can extend this list to a basis. However, 2.34 says that any two bases have the same length. This implies this list is made a basis by adding 0 vectors, so it's already a basis. By the same logic, we can also prove that if we have a spanning list that is short enough to match the dimension of the space, then it's automatically a basis. We won't go over the proof here, but you can give it a try. You can find the proof in the text as well. Finally, there's a theorem that tells us how to calculate the dimension of the sum of two vector spaces. It's very similar to the union of two sets. We won't be going over the proof here. It's nicely presented in the text. Here are the exercise problems for this chapter. Again, give them a go if you want to spot the holes in your understanding. I want to conclude this video by summarizing the concepts we've covered in this chapter. We started by visualizing the concept of vectors spanning a space and how that's leveraged to define dimension. And then we introduced the concepts of linear dependence and independence. After that, we combined all the previous concepts to define bases. Lastly, we formally defined dimension as the length of a basis. And that concludes chapter 2 of this series. Don't forget to support the channel by hitting the like button and subscribe. It really means a lot to me. Alright, I'll see you in the next episode.